Come on. Okay, we're recording. All right. So I'm trying this board today. We're really for two reasons. One, because of a nice birthday message that's written on the Everboard. I don't feel like erasing so quickly. And I haven't been happy with how the video looks. So I'm curious to see if using this half board works out better. We'll see. I got to be ready to take pictures. Okay. Now, as far as how the covered material relates to the homework problems, last week was finite difference. So that would, so after last class, you would have seen enough material to do the first homework. So that's problems 1, 2, and 3. Even with the material fresh in your mind, problems can still be a pain. And I'll probably have to carve out some time in class later to focus on that. So this week is spectral methods, and that will relate to homework 2. And so today and Thursday are covering that. Also, I think you all got my message. Did I send a message yesterday in Canvas about Thursday's class? Because I know I meant to, but I'm not sure if I actually did. What?
I didn't get an email about it.
Yeah, I haven't checked Canvas itself, but I didn't get
Okay.
an email.
Because let me check what I did in Canvas. Okay, no, that's right. I have not gotten around to it yet. But again, you're all here, so I can tell you here. So Thursday's class will be virtual for everyone because for my other class, 460, 560, I have students at the Gulf Park campus. So a few times a semester, I like to go down there so that at least some of the time they can have the in-person teaching experience. So I'm going to be at Gulf Park most of the day. So there's no need to come to this room because I won't be here. And then so a few Thursdays during the semester, I'll be doing that. And I was supposed to give you a heads up, and I think I'd even started the message in Canvas and just never finished it and sent it. So whoops. But now you know. All right. Okay, so interesting finite difference methods, which are certainly conceptually the simplest methods for solving ODEs and PDEs, because you're representing all the derivatives using an expression that relates to the definition of a derivative that you're familiar with since Calculus 1. But there are all kinds of categories of methods for solving PDEs. We're only going to see some of them during this course. Some mainly finite difference, spectral methods for spatial derivatives, and later I'll be talking about various methods from ODEs for the time stepping part when you have time dependent problems. So I'm going to discuss spectral methods as a contrast with finite difference. So the error in FD, I'm being lazy, that's my acronym for finite difference. Well, that's the acronym for finite difference. As we've seen last week, it's a power of H, where H is whatever grid spacing you're using. For instance, the scheme I showed last week for Poisson's equation, we used a center difference for UXX. So we have had second order accurate. So the error in that scheme was order H squared. Okay. And the important thing to point out here is that P is some fixed value, generally an integer. So it just depends on what scheme you're using. What finite difference formula are you using to approximate any derivatives? And that's going to determine the value of P. Okay. Now, by contrast, the error in the methods that I'll be covering this week, spectral methods, is order h to the p, but for any p. So the error actually goes to 0 faster than h to the p. So there's still a notion of a grid, and therefore a grid spacing h. But whatever value you pick for p, like h to the 100, it's possible for the error to go to 0 even faster than that. So you have much more rapid convergence. Okay, so another way of putting it is the error goes to 0 exponentially fast. Okay. All right. Now, well, I'd be careful about when this actually applies. There is a caveat here. If the solution U is infinitely smooth. So that's important. Now, that's not an unreasonable assumption. There are very important PDE whose solutions are infinitely smooth. Heat equation. So any diffusive problem, you do have that infinite smoothness. Okay. Now, what if it's not true? If U is in CP, in other words, the definition of CP, of function space, it's space of all functions that are p times continuously differentiable. So if U belongs to CP, but it does not belong to CP plus 1, so there are only p derivatives that are continuous, then it's more like finite difference. So it's order h to the p again. So for example, advective problems, a wave equation. If you have initial data with limited smoothness, then the solution will inherit that limited smoothness. So spectral methods won't be as accurate in that case. Okay. All right. Okay. Now, so there's a trade-off here with spectral methods versus finite difference. So, and other classes of methods that I could talk about, like finite element, finite volume, etc. So limited use. They're good for problems on nice domains. And instead of simply writing what they are, I will draw them. Rectangles. Circles, that's supposed to be a circle. It's a terrible circle. So domains that can be easily described, whereas some shapeless blob, finite element methods are really good for that. Spectral methods, not really. Okay. Also, they're best for linear PDEs and simple boundary conditions. Okay. Now, there actually is one other qualifier that I could have written here. That is not just linear PDEs, so PDEs of constant coefficients. But that's not really true anymore because of my spectral methods. So if you know anything about my research program, for my dissertation, I developed a class of spectral methods, pre-love subspace spectral methods. Now, like other spectral methods, they are subject to these same limitations, although in recent work have moved beyond restriction of simple boundary conditions. For example, non-homogeneous boundary conditions can handle those problems just fine. Actually, can still be used for nonlinear PDEs in combination with other numerical methods. Although a version of KSS methods that by itself can be used very effectively for nonlinear problems is now being developed and will be implemented soon by our own Bailey Rester. So, so yes, I'm doing my best to, me and with my students, overcome these limitations of spectral methods. Now, for problems for which spectral methods are applicable, they really are the most effective because of this rapid convergence. All right. So that's why spectral methods are still quite popular, because there are problems of importance that fall into this seemingly narrow, fit in a seemingly small box. So it's still a very active area of research. In fact, there's a conference that's held every 2 to 3 years, the International Conference on Spectral and Higher Order Methods, that I frequently attended in some very interesting locations. Okay, so my plan for today is to deal with problems with periodic boundary conditions, and that's Fourier spectral methods. And then on Thursday, if I get through periodic on today, Chebyshev spectral methods for problems with non-periodic boundary conditions. Okay. All right. Okay. There's one other, before I get into spectral methods, I want to make one other contrast between them. Spectral versus finite difference. Finite difference methods are local. Spectral methods are non-local in approximating derivatives. Now, what do I mean by that? That's okay. When you're approximating a derivative, we saw what was a standard difference for second for uxx. You're trying to approximate a derivative at a certain point, and you're using the value of the function at that point, and the point to the left and the point to the right, and only those points. That's a local approximation. So finite difference generally is local. It only uses approximate derivative at a point, only uses nearby points, which makes sense. That why it might be effective, because the derivative is a local quantity. You're taking f of x plus h minus f of x over h as h goes to 0, so it's only based on local behavior. Spectral methods, on the other hand, to approximate a derivative at a point, will use all the points on the grid. Now, that seems horribly inefficient, but what we'll find is that it actually can be done efficiently. And that's what leads to this far higher accuracy, much more rapid convergence than in the case of finite difference. Okay. So this is the summary of the contrast between these two families of methods. So now what I'll do is get into case of periodic boundary conditions. Okay. Any questions before I erase? All right. In fact, I haven't really gotten to anything yet. So this is a ranting part of class. Oh, I've got to take a picture. Okay, so okay. So let's suppose we have a function u of x assumed to be 2 pi periodic. Now, and I can express u of x in terms of its Fourier series. I'll use the complex exponential form. That'll be more convenient for what we're doing, as opposed to sines and cosines. Okay, and the Fourier coefficients, the UK hat, are defined as follows. As an integral okay. All right. Now, but the thing is, this is not something I could compute exactly. So, right. So certainly we're working with this function in a discrete setting, where we don't have a formula for u of x. What we have is the values of u of x at certain grid points. So our discretization of u of x is uj, which is the value of u at a grid point xj, what I've done here is I've substituted x equal xj into the formula for a Fourier series, but I've also limited myself to this range of n, capital N total frequencies. So, okay. And j ranges from 1 to n. And my spacing, xj is equal to j. So I'm going to check my notation here. H. Okay. No, I just realized I don't think I've actually defined the grid spacing. Oh, I have, yes. On the previous page. So these are my grid points, j times h. H is 2 pi over n, because we're dealing with a function defined on the interval 0 to 2 pi. It's 2 pi periodic. Now, notice I've left out x equals 0, the left endpoint. But that's okay, because I do have the right endpoint, x equal 2 pi. And u is periodic. So the value of u at 0 is the value at 2 pi. So it's still accounted for. So when you're dealing with periodic functions and you use a grid, you only include one of the endpoints. I've seen some books include the left, these notes include the right. So either or, as long as you're consistent. Okay. And then UK hat is defined in a discrete fashion, also using these values of u on the grid. Okay. where k ranges over these frequencies. And I'm assuming here that n is even. So we want the range of k values to be as symmetric around 0 as possible. So because n is even, we do have one more positive frequency than negative. Okay. So what we have here, to compute these coefficients these are approximations of these integrals. So this is the discrete Fourier transform. Okay. All right. Okay. Now the nice thing is, now we do have n of these to compute from these n values of u at the grid point, on the grid points. Now normally, to compute these n values from these n would involve a matrix vector multiplication, where these values here have matrix entries. That's order n squared work, but we don't have to do that much work because we can use the FFT, fast Fourier transform, and that has on the order of n log n. Flops is short for floating point operations. So n log n arithmetic operations are needed to compute these Fourier coefficients from these grid points, or vice versa. We could go in either direction. That would be an inverse FFT. So that's much faster than a ordinary matrix vector multiplication. So at least we can go back and forth efficiently. Okay. Right. Questions up to this point? I should mention that there actually is a theorem that actually from I saw in a book that was co-written by my first advisor, Joe Oliger. Actually, the book I learned from was Time-Dependent Problems and Difference Methods by Bertil Gustafsson, Heinz Otto Kreis, and Joe Oliger. So they're all Swedish people, so Oliger was my first advisor. Gustafsson was his academic brother, and Heinz Otto Kreis was the advisor for both of them. And his daughter, Gunilla Kreis, is who I learned much of numerical linear algebra from at Stanford. So first Dean Golub, I took his course, and then her course all about. So she's who I learned the QR algorithm from. Okay. So anyway. So in his book, in their book, there's a theorem that relates these Fourier coefficients, the discrete version, to the continuous version here that comes from the integral. So in order to express that, I need to use different notation for one of them. So what I'm going to do is I need to keep working with these. So I'll leave this as UK hat. I'll call these UK tilde. So there's less editing in your notes and on my board. So how do UK hat relate to the UK tilde? Actually, I hope I can remember the formula, but it's also mentioned in my book. But UK hat is equal to a sum, all going from minus infinity to infinity, of U tilde K plus L N. Okay. So each one of these discrete coefficients is equal to a sum of infinitely many of the continuous coefficients, but spaced and apart. Now, what that would mean is if UK tilde is 0 outside of this range of K, then UK hat and UK tilde are equal. So that's what we prefer to have happen. Now, generally, as K goes to plus or minus infinity, these coefficients go to 0 anyway. So, well, most of the time, UK hat is a very good approximation of UK tilde. How good approximation is it? It depends on how smooth the function u of x is. So the smoother it is, the better approximation UK hat is of UK tilde. But these other coefficients that are lumped into this sum for L non-zero, you can think of them as an error. And if u is not so smooth, that error could be substantial. So what happens is higher frequency content of u of x is assigned to lower frequencies. That's what this summation is saying. And this is a troublesome phenomenon called aliasing. Because u really consists of infinitely many waves of frequencies going from minus infinity to infinity. So the discrete Fourier transform is taking content in waves of really high frequencies outside of this range and saying, oh, you can't be at that frequency, move to this one. And all that gets added together. And sometimes that can lead to, like for functions of jump discontinuities, it can lead to large errors. That's where Gibbs phenomenon comes about, where if you have a function as a jump discontinuity and you compute its Fourier series, your discrete Fourier series, then when you graph it, you'll find these high frequency oscillations near the jumps, and then away from the jumps, it's fine. But that's a big problem. So Fourier series are definitely far more effective for smooth functions. Okay. All right. But the goal here, what we want to do with this representation of u, is come up with a scheme for approximating the derivative of u with respect to x using all of these points to get as much accuracy as possible. Okay. All right. Now, okay. Now, generally, any method for approximating a derivative has this approach where what you do is you approximate your function. Or the approximation is a particularly simple function to work with in terms of taking derivatives. And then you take the derivative of that approximation exactly. So the approximation of a derivative literally is the derivative of the approximation. All right. So to approximate u prime of x where u is equal to this Fourier series of infinitely many coefficients, and those are written, you take k tilde there, that's the exact Fourier series of u. What we do is we compute the exact derivative of this function, p of x, which has a similar form, but we use UK hat the discrete Fourier transform, and k is limited to n frequencies. Okay. And this function is called the band-limited interpolance of u of x. Also referred to in the notes as the BLI. Okay. So in this sense, spectral methods are not, conceptually not that different from finite difference methods, because finite difference methods, what you're doing is you're approximating your function by an ordinary polynomial and taking a derivative of a polynomial exactly. All the finite difference rules we've seen come from that approach. Here, instead of an ordinary polynomial, we're using a function of this kind, which is called a trigonometric polynomial. Because we have here e to the ix raised to powers where k is the exponent. Okay. And both kinds of functions, regular polynomials and trigonometric polynomials, are very easy to differentiate. So it makes sense to use functions of either type for approximating derivatives. Okay. So it's a trigonometric polynomial. Okay. Now, to help me do this, I'm going to define this delta J be the discrete delta function. Earlier, I think it was a couple weeks ago, you'd seen the Dirac delta function, a function that is equal to 0 whenever its argument is non-zero. So this is a discrete version of that. Delta J is defined to be equal to 1 if J is equal to 0 mod n and 0 otherwise. Okay. So then what I can do is I can express uj, my value of u at each grid point, as a sum as a linear combination of all the u values times this discrete delta function, because this is going to be 0 unless j minus m is a multiple of n. So it has the effect of selecting uj from this. Okay. So now what I can do is express p of x in terms of the delta function. Okay. Because so this is the band-limited interpolance of delta J. So, because this interpolates delta J, it is equal to 0 whenever x is any of the grid points other than xj. So what I would need is, so for instance, if I set x equal to xj, so I'll have xj here, then only when xm is equal to xj will I get something non-zero, and that would have, so I'd get uj out of the whole summation. So I've already defined P of X this way by truncating the Fourier series of U and using the approximate coefficients. It actually is easier to work out what the derivative of P of X will be by writing it this way. Because now all I have to do is, if I want to take a derivative of P, I just need to take a derivative of these. Okay. All right. Okay, this will be a good break point.
I'll see two of these on the back. So, Shannon, your design on the board is a lot nicer than mine would have been.
Not the greatest, but I guess it's nice and fun. Oh, I can erase that. That would be great. I'm gonna erase it. Pulled it out, and I was like, oh,
He
it's
walks
not
in
good
and
enough.
it's just gone.
Yeah, I don't think they go wrong.
Yeah, have some cupcakes. Dr. Lambert said that it's way too many. I brought myself a cookie.
They're so small that like, I just shove it all in my mouth at once.
Right?
Yes.
Oh, I'll try the next one.
Pretty good.
So Rachel's tutor is superior. I don't know why, but their Cal 1 instructor is teaching them epsilon delta proofs for limits. So one of the students that Rachel was, I was telling her one of the students that Rachel was tutoring earlier for Cal 1, their instructor was teaching them epsilon delta proofs for limits.
Yeah, I think that was better.
Was it?
Yeah, I saw students in the comparison class and he gave them a note to prepare for the test home and he asked them to learn the epsilon delta.
Like, I did not learn that until like my junior or senior years in undergrad.
Yeah, same.
I think I learned that in my first after school. I didn't understand what it was.
Yeah, the calculus course I had my freshman year of undergrad did not even touch that. It wasn't until I got to, I think I learned it like 461 that I took when I was a junior or senior medicine.
After I struggled with that first in my first year. The going on this also my second year and still what was being done. I began to wonder what was it about this my first year. I didn't understand. Yeah. You want to say giving epsilon. Say find the secret of delta. I didn't understand what I didn't understand what we're doing.
Yeah, that's what you asking me to do, and I'm like, yeah. And I'm just thinking like, yeah, I did not learn that in Cal 1.
Okay, thank you for being a little helpful. Never has 5 minutes passed so quickly than when I go take a break in the middle of class. Like I reach my office, play my phone for what feels like 30 seconds, and then bam, 5 minutes are up. Okay, now, so from how I wrote P of x before, what we want is U prime at xj for each j. So that would be, so approximately equal to the sum of U m pj prime xj minus xm. So all I did was I took a previous equation that I just erased, took its derivative, and then set x equal to xj. So this is exactly equal to p prime at xj. Now the reason why I've written it this way is, well, these are numbers. Once I have these numbers, those are the coefficients of um in my differentiation rule. So in that sense, it's very similar to finite difference. Finite difference method, you are taking certain values of u at grid points and multiplying it by coefficients and combining them to get approximate derivative. It's the same approach here. I want these coefficients. The difference is, with finite difference, you only have a handful of points. Here it's going to be all n points. All right. So how do I get those? All right. Okay. So here I'm using the fact that Pj is the interpolant of delta j. Now, the discrete Fourier transform, DFT, of delta j is as follows. Delta k hat is, so I'm using a formula for the discrete Fourier transform, e to the minus I k xj times delta j when I'm taking the discrete Fourier transform up. But this is equal to 0 unless j is equal to 0 mod n. Well, the only time j is equal to 0 mod n is when j is equal to n. So that's going to be h times e to the minus ik times the last grid point, which is 2 pi, and then delta will be equal to 1 at that point. But what is e to the 2 pi minus ik, where k is an integer? That's important. I can write it this way. So focus on this. What is that equal to? It's 1. So this is actually 1. So it's just h. In other words, all of the discrete Fourier transform DFT coefficients of delta j are equal to the same value, h. And this applies for all k in range. Okay, so that very simple expression for delta k hat will be helpful to us. So, therefore, pj of x, that's equal to 1 over 2 pi sum over those k of delta k hat e to the ikx. Because this is the band limited interpolant of delta j that I'm looking for. So now, all I have to do is fill in that this is equal to h. So this is h over 2 pi times the sum of e to the ikx. Okay. So now the question is, what is this? Well, what I can do is I can break down this complex exponential as sines and cosines. So I have cosine kx plus I times the sum sine kx. So now it becomes easier to work with cosines and sines individually than the whole matrix exponential. But the thing is, pj of x is a Fourier interpolant of a real valued function. Therefore, it should also be real. So it would actually follow from that this part is 0. I mean, it can be shown in a more direct way, but the bottom line is it turns out to be 0. All right, how am I doing on time? All right. Now, okay. So now I want to know what's the sum of all of those cosines. Now, unfortunately, I won't have time to go through the whole thing here. But what you do is you use trig identities, because this is equal to a sum of cosine kx where k is an integer, and I actually have a trig identity that's in the notes that you can use to work out what this is. Basically, what you do is you multiply and divide this by sine of x, and then you use what's called a product to sum identity and also a sum to product identity. And what ends up happening is that pj of x is equal to, okay, h over 2 pi sine of pi x over h all over tangent of x over 2. So all right, so like I said, the notes have some information about which string identities are used. What I would like to do, and I hope to have time to soon, is sometime when I post the notes, actually work out the whole thing, so you can see how we arrive at this expression. Okay. So now I have this formula for Pj of x. So in other words, if I plugged in any grid point xj into here, what would happen is I would always get 0 unless j is equal to 0, in which case I would get 1. I should mention that if I plug in x equals 0, we have a 0 over 0 situation. But if you would take the limit as x goes to 0, you would end up getting 1. Okay, so it's because of this coefficient down here that makes it equal to 1. Okay, because as x gets smaller and smaller, sine x approaches x, or behaves like x. Tangent x also behaves like x. So as x goes to 0, effectively the sine and the tangent go away, and if you were to cancel these, you would see the x's cancel, and you'd have 2 pi over h. But here you have h over 2 pi. So the limit as x goes to 0 is 1. All right. On the other hand, if you plugged in x equal to any other grid point, xj is equal to an integer times times 2 pi over n. Right. Actually, more of a point, xj, any grid point xk is equal to k times h. And so that h would cancel the h here. So then you'd have sine of pi times an integer, which is 0. All right. So if I go back to my approximation here, this is what I'm looking for. And it's equal to this sum, where now I have a derivative of Pj of x evaluated at this point. So now what I have to do is I have to take the derivative of this. And then once I finish taking derivative, substitute x equal to this. Now, taking a derivative of this, naturally that's going to require a product rule. That's a product rule, quotient rule. Okay, technically it's also a product rule, but what I'm actually going to use is a quotient rule. Okay. So I'll leave this up here because this is what I'm after. So Pj prime evaluated at a grid point xk is equal to Bj prime of KH. So by the quotient rule, applied to the formula I just erased, we have tangent KH over 2 cosine pi k times k over h, where I've substituted kh in for x. That's very important. Minus sine pi k secant squared kh over 2 times 1/2 all over tangent squared kh over 2. Okay. Now, it turns out this whole expression simplifies quite a bit. For one thing, actually, can anyone tell me what things in this expression simplify? You know that k is an integer. Yeah, this is 0. That's gone. What else?
Pi over h.
Oh, so sorry, what?
You have k over h. Turn that is pi over h.
Sorry, I may have read my notes wrong. Let me check. Yes, it is pi over h. Sorry, my glasses fog up. Okay, what else simplifies? Okay, cosine of pi k, what is that equal to? Yeah, so this is equal to -1 to the k. All right, so this whole thing condenses to 1/2 -1 to the k, because the pi's cancel, the h's cancel, and you get cotangent of kh over 2, because this tangent cancels with one of the ones down here. So you're left with 1 over tangent, but that's cotangent. Okay. So now what I can do is I can use this up here, because this is equal to h times j minus m. So now I have my endpoint stencil. Remember, finite difference methods, we had a stencil, which was just basically consisted of a coefficients that you multiply values of u by to get the derivative. Same thing here, only whereas finite difference stencils only had a very small number of points, this one has n points. U prime is equal to 1/2 of the sum of -1 to the j minus m cotangent j minus m h over 2. Okay, so this is your coefficient times um. Okay. So if you take this linear combination of u, evaluate all your grid points, then that is a highly accurate approximation of u prime at xj. So that is our differentiation rule for periodic functions. So what you could do is you could describe this as a matrix vector product. So another way of writing it is u prime is equal to a matrix times u, which consists of vector u. It consists of all the divisor u at all the grid points, and the coefficients that go in here fill the matrix. And because it depends on j minus m, it's actually, you think of the banded matrix. Okay. In other words, okay, really, because the entries depend not on j or m individually, but rather the difference, j minus m, all the entries down a given diagonal are the same. You actually have zeros down the main diagonal. On the super diagonal, you have 1/2 cotangent h over 2. The diagonal below, you have minus that. So if a matrix is skew symmetric, this matrix is equal to the negative of its own transpose. If at the next diagonal you'd have -1/2 cotangent 2h over 2, and then 3h over 2, and so on. Okay. Another term for this is a Toeplitz matrix. So Toeplitz matrix in general has all the entries down a given diagonal being the same. So this matrix is called a differentiation matrix. It's a matrix that you multiply a vector by it represents a function to get the values, approximate values of that function's derivative. Now, finite difference, we also had differentiation matrices. But those were like tridiagonal, for instance, or bidiagonal. Here, this matrix is full. Nearly all the entries are non-zero. Now, that sounds inefficient. Like to do a matrix vector multiplication by a full matrix, that's order n squared operations. But it's actually possible to do this efficiently, as I said, using the FFT instead of multiplying by this matrix directly. All right. Okay. Now, the accuracy. From the order of h to the n, because we're using n points. However, let's not forget, n is related to h. So that's order h to the 1 over h. So as h is going to 0, the exponent's getting larger. So convergence is getting even faster. So this is what I mean by convergence happening faster than any fixed power of h. So that's the beauty of spectral methods, so that at least for smooth functions, can get extremely high accuracy. Okay. Questions about what happened here? I know it's quite a mess. Some of the key ideas here were to express the value of u at each grid point as a linear combination of the values of u at all the grid points, using the Dirac delta function, at least a discrete version of a delta function. So then to take a derivative of u, you figure out the derivative of a discrete delta function, or at least a trigonometric polynomial approximation of a discrete delta function. So that's all. Really, that's what we're doing. We're writing u as a trigonometric polynomial. So to approximate the derivative of u, we take the exact derivative of the trigonometric polynomial. So what I can do is show you another way we can get the derivative that's actually more efficient in practice, but is mathematically equivalent to this. And for that, we return to the band-limited interpolant. Okay. All right. So the FFT version of approximating a derivative. So u of x is approximated by its band-limited interpolant. I'll just repeat that formula here. Okay. Therefore, u prime of x is approximated by p prime of x And if I want to take the derivative of this, oh, I think I forgot the factor of 1 over 2 pi. Okay. How do I take, what's the derivative of this with respect to x? Yeah, I multiply by ik. Okay. So here's an algorithm we could use. So first you apply FFT on the vector of values uj. I'm writing this one, but this is a vector you're working with. And that produces a vector of discrete DFT coefficients, uk hat. Second, you take those coefficients and you multiply each of them by ik. So this gives you the DFT coefficients of the derivative. And then you do the inverse FFT of the scaled coefficients, and that gives you approximations of uj prime. So take a fast Fourier transform, scale the coefficients by ik for each k, take that, apply the inverse transform to that, and what comes out of it is values of the approximate derivative at the grid points. So this whole process, the most expensive part is the first and last steps. You're doing a fast Fourier transform. So this whole process takes order n log n floating point operations. Whereas if I formed that matrix and use that, which is mathematically equivalent, that's order n squared operations. Okay, but I want to show you, here's what the stencil looks like for this process to contrast with finite difference. Okay. So certain PDEs of a simpler form can be solved very quickly using a process like this. There's actually an example at this point in the notes where I have a PDE in 2 dimensions of this Poisson's equation in 2 dimensions, where I pretty much do this sort of thing where I take the 2-dimensional FFT, scale the coefficients accordingly, and then do the inverse 2-dimensional FFT to solve a PDE. So even though we have full matrices versus sparse for finite difference, we can still solve PDEs very accurately, very efficiently. At least those PDEs for which spectral methods are effective. Okay. All right. Now, are there any homework questions? Okay, let me refine my question. Have all of you at least been gotten started on number 1? Finished number 1. Oh, okay.
I am mostly finished with number 1.
Okay.
So we made progress.
All right. Has anyone looked at any problem past number 1?
Started on number 2.
Okay.
That is a no from me.
Okay. Yeah. Well, I mean, I only just covered that less than a week ago, so. Okay. I can see what I have coming up as far as covering stuff. Okay. Spectral methods this week. Oh, wow. I really blew it as far as the schedule is concerned, although it's not a bad thing, really. For some reason, I thought that I needed to get through all of Chapter 3, Spectral Methods, this week, meaning periodic boundary conditions all today, and then Thursday, non-periodic boundary conditions. but that's actually not needed to be covered until next week. So there's nothing more I urgently need to cover this week. But what I will do is there are certain things I glossed over today because I thought I had less time than I do. So I will take care of that on Thursday. But then that would mean that there would be some time for homework questions. So if you can, see if you can, if you haven't looked at number 2 yet, see if you can get going on that, and we can take some time to talk about that on Thursday. So, and as a reminder, Thursday's class is virtual. So I'll see y'all on Teams.
Bye, Dr. Lambers.
All right.
And happy birthday.
Thank you. Those of you here, please take some cupcakes.